of the cell phone formed inside a polyhedron. Now I want to introduce my motivation. When we dip a wireframe of a tube in soapy water and put it out, the cell phone form does not affect at all. What is causing this, and how do we understand it? This puzzle motivated me to design this experiment and seek a reasonable theoretical explanation. These are our purposes. First, what is the shape of the cell phone? Second, how can we conveniently measure the curvature of the cell phone? Third, what factors affect the shape of the cell phone? Fourth, how do we understand it theoretically? These are our procedures. First, we dip a cubic wireframe made of copper into soapy water and pull it out. The shape of the cell phone forms can be different each time we do the experiment. Second, to see what may be causing the difference, we tried varying the temperature and the concentration of the soapy water. Third, we developed a simple theory to explain why we observe shape of the cell phone by vary a lot under seemingly same conditions. Now let's get into the details of the experiment. At least our flowchart. For tetrahedra, groups, and octahedra, tilting angles such as 15 degree, 30 degree, 45 degree, 60 degree, 75 degree, and 90 degree are investigated. For change the ratio of composition. For cubes, face tilting angle vertically and rise temperatures to 15 degrees Celsius, 25 degrees Celsius, and 35 degrees Celsius. Change the size of the cube model to 10 centimeters and 20 centimeters. For models with a diameter of 1.5 millimeter and 0.4 millimeter, lower temperatures to 0 degrees Celsius and minus 3 degrees Celsius. By using side of the central square, determine the sum of the areas of one square for triangles and 8 trapezoids. Consider the central square forming a curve for force equilibrium and determine its curvature using quadratic approximation. Measure and calculate angles between the planes where central square and two adjacent trapezoids located respectively. At an early stage of the experiment, we actually built and tried out wireframe models for tetrahedra, cubes, and octahedra. However, we quickly realized that the shape of the cell phone can be quite complicated. We therefore decided to settle for cubes for now, hoping that a better understanding of this simple system will eventually help us to extend our experiment to other models. To check how temperature affects the formation of the cell phone, we heated up the soapy water. We found that the shape of the cell phone is unstable, so we used ice cubes and salt to cool the cell phone. But generally, we found that temperature is not a crucial factor affecting the shape. We also vary the diameter of a copper wire and the concentration of the soapy water. But once again, they do not seem to affect the shape of the cell phone either. We now move on to what we found about the shape of the cell phone and how we observe and analyze it. Step 1. We enlarge our photo and adjust its orientation so that the upper edge of the central square becomes horizontal. Step 2. As a first approximation, all the surfaces connected to the central square can be approximated as a trapezoid. This is mathematical simulation of calculating the sum of the areas of one square for triangles and 8 trapezoids. This figure shows the relationship between x and f of x. Because the cell phone has the tendency of minimizing the surface area, we may compute the total area of this configuration and set it as the function f of x of the length s of the square edge. Ideally, we expect the cell phones to settle down to the x, which minimizes the area. Then kind of surprised, we found that f of s is a very insensitive to change in x. For instance, from this figure 1 hardly suspect there could be any minimum because it looks so flat, for as ranging from 0 up to 20% of the side of the wireframe. Only when we learned the portion near x is 0.07291 and we up to 5 significant digits, did we see a dip in the curve. What this implies is that, experimentally, we won't be able to see the same fixed shape every time, because the many shapes share almost the same minimum energy. Indeed, it was observed early on our experiment and was quite a puzzle to us. But now, after this simple analysis, we seem to understand better why this should be the case.
棒子可以放下来，要讲注意。
If we look closer, we also see that the central square edge is not really a straight segment, but this is understandable because when three surfaces intersect at an edge, the angle between any two must be 120 degrees, and this cannot be strictly satisfied in our current configuration. This then implies that the supposedly straight edge should be slightly curved in theory. And this is what makes this investigation even more interesting. And here is a little animation showing how the balance of the three forces requires the common edge to be curved.
你可以用手，到时候万一太小的话，
这个可以放大。
对，可以放大，对。
这个不是很熟悉，我等下再用。
好，你待会再练习，待会再练。
Now we are talking about the edge of the face squared. Once we realized that the square edge should be slightly curved, it is only nature to assert that the other trapezoid we discussed above actually are slightly curved surface too. Therefore, determining their curvature becomes an even more challenging task. This table shows the result of our experiments, including the length of the square and the sum of the areas and the curvature of the side of the face squared. Finally, we wanted to find the angle of the plane where the central square and two adjacent trapezoids. These two columns shows the angle with two pictures, and this column shows the angle of the three adjacent planes. We use the following equipment. We take points from two angles which are vertical, and the x is the edge of square. F of x is the sum of the areas. This table shows the result of our theory experiment. According to the experimental observation, those factors don't seem to affect the size of the central face square. We ever wonder even if the experimental felt why the size of the central square change under different conditions. In three prior findings, we actually just start a new series of experiments to determine the true shapes of the trapezoids. Because these surfaces are quiet at first sight, we have employed the concept of optical lever. In the experiment, the schematic of this experimental setup and the actual photo are shown here. The following are our conclusions. First, up to now, we have demonstrated that the shape of the soil film is not sensitive to temperature variations or the concentration of the soapy water. Second, as far as the central square is concerned, its size tends to vary a lot when we repeat the experiment. But we now understand that this is caused by the fact that the surface energy as a function of the size has a shallow minimum. Third, the trapezoids adjacent to the central square are not true planes. Now we are talking about our future work. Basically, a surface is illuminated by a linear light force, and the reflection from the surface is recorded. As this photo shows, the reflected image becomes curved and enlarged. This enlargement presumably will allow us to reconstruct the shape of the reflecting surface with a better precision. We are still on our way of establishing the needed analytical tools to complete this challenging but rewarding task. Thank you for listening.